We want to find the equation of the line tangent to f of x equals 6x plus 4 over x plus 9 at the point 1, comma 1. So to find the equation of any kind of line, we need two things. We need a point, which we have, and we need a slope, which we're going to find. And the way we typically find the slope is by finding the derivative and plugging in the point. So we're going to find the derivative here using the quotient rule. So our derivative is going to be the bottom times the derivative of the top, which is 6, minus the top, times the derivative of the bottom, which is 1, all divided by the bottom squared. Generally, I would probably prefer to simplify this. Like, if I simplify this pretty nicely, but here's the thing. I don't really care about simplifying this because I really only care about the slope of the tangent line at the point where x is equal to 1. So while you could simplify this, I'd rather just find my slope, which is going to be f prime of 1, which is going to be 1 plus 9 times 6 minus 6 times 1 plus 4, all divided by 1 plus 9 squared. Or in other words, it's going to be 10 times 6 minus 10 all over 10 squared, which is going to be 50 over 100, which is 1/2. I will say, just for those of you curious, we could have simplified the top here. It would have been 6x plus 54 minus 6x minus 4 all over x plus 9 squared. And you can actually cancel the 6x's here and just get 50 over x plus 9 squared. We didn't need to do that work to be able to plug in 1. So I'm all about trying to not do more work than we really need to for these problems. Okay, we've got the point, we've got the slope. Now we're just going to throw that information into the point slope form. So I'm going to write y minus the y coordinate equals my slope times x minus the x coordinate. And then usually we are asked to write or solve for just y. So I would rewrite this as y minus 1 equals 1/2 x minus 1/2, and then add 1 to both sides to get y equal to 1/2 x plus 1/2. Questions about that? Let's try another one. And then you all try this next one. So f of x equal to, sure, 2x plus 3 to the 5th times 3x plus 4 to the 3rd. Find just the slope of the tangent line at the point -1, comma 1. I guess you wouldn't really need to know the y coordinate there, but there it is anyway. Give that a shot. Take the derivative using the product and the chain rule. And then after you've differentiated, plug in your point. I should give people on Zoom the chat, the attendance form. All right, let's take a look. We start taking the derivative. We're thinking of this as one piece. I'm going to call it U since I've already used F. And this is another piece, V. We're going to use the product rule. F prime of X is going to just equal U prime times V plus U times V prime. So in this case, that's going to be the derivative of 2x plus 3 to the fifth, which means we're going to have to use the chain rule. So we have some stuff to the fifth power. The derivative is going to be, well, the derivative of x to the fifth is 5x to the fourth. So there's some stuff to the fifth. It's going to be 5 times our stuff to the fourth multiplied by the derivative of the stuff. So that's our u prime. Again, you don't need to label these things these ways when you do this. I'm just labeling it so we can see what's what. And then we're multiplying that by v left alone, 3x plus 4 to the third. And then we add and we switch it up. You leave u alone, so we have 2x plus 3 to the fifth, multiplied by the derivative of v, which is going to be, so I've got some stuff cubed. The derivative is going to be 3 times my stuff squared times the derivative of the inside stuff, which is another 3. So there's my u, and there's my v prime. And again, since we're finding the slope of a tangent line at a particular point, after you've differentiated, you can just plug in the point. So I'm just going to plug in x equal to -1 and see what I get. So f prime of -1 is going to be, now let's be kind of smart about this. If I plug in -1, I see that -1 times 2 is -2 plus 3 is 1. And 1 to any power is also 1. So when I plug this in, I'm going to get 5 times 1 to the fourth times 2 times also 1 here, 1 to the third. Plus over here, I'm going to get 1 to the fifth times 3 times 1 to the second times 3. So simplifying this, I have 5 times 1 times 2 times 1 plus 1 times 3 times 1 times 3. So 19. And my slope of the tangent line is 19. And if I was asked to find the equation of the tangent line, it would be a straight shot from there. I would take my slope, I would take my point, and I would use the point slope form and do y minus the y coordinate equals 19 times x minus the x coordinate. And then we could simplify. Be careful. I've seen people, when they do this, take this equation on the right-hand side and kind of forget to distribute the 19 or whatever you have there. So we really should write this as y minus 1 equal to 19x plus 19 times 1. And then we can add 1 to both sides and get y equal to 19x plus 20. So that would be, now that we were asked for that, but that would be the equation of the tangent line at that point if we wanted to find it. How did I get 19? Let me make sure I didn't do anything incorrect. So I'm plugging in -1. And so I kind of skipped a step. What I really had here was 5 times -2 plus 3 to the fourth times 2 times 3 times -1 plus 4 to the third plus -2 plus 3 to the fifth times 3 times -3 plus 4 squared times 3. But then each of the things in the parentheses, and I picked this on purpose, each of the things in the parentheses is just 1. -2 plus 3 is 1, -3 plus 4 is 1, and 1 to any power is 1. So what I have here is 5 times 1 times 2 times 1, and 5 times 2 is 10. Over here I have 1 times 3 times 1 times 3, and 3 times 3 is 9. And then 10 plus 9 is 19. Other questions about this? All right, let's take a different tack. And this is actually a question somebody, this is a slight variation on a question somebody asked me about. So let's say we're given the equation 4x cubed plus 30x squared times y plus 5xy squared. I'm going to change this number over here. It was a 5 in the question. I'm going to change it to a -21 for purposes you will see. And again, we're going to ask about the tangent line. We want to find the equation of the line tangent at the point What was it here? I had 1, -1. Not every point's going to be 1, 1 or -1, 1 or whatever. It's often very easy to use that point because it's easy to make things work if everything's 1. But it could be something else like 2, 5 or whatever. So the difference between this problem and the previous problems is we don't have y as a function of x or just f of x. We have y's and x's mixed up together, which means we have to use the process of implicit differentiation. So when we take this equation here, 4x cubed plus 30x squared times y plus 5x times y squared equal to -21. The first step is going to be to differentiate both sides, assuming that everything is a function of x. So when we look at y, and again, we talked about this on Tuesday, where we're saying like y is a function of x, or as I would say, our y is some stuff. So it's like the inside of a function whose derivative we're going to have to multiply by. All right. One other thing I would say before I get going here is the derivative of 4x cubed is going to be fine. It's going to be 12x squared. But for this 30x squared times y, I see that I'm going to have to use the product rule. So I have x squared, a function of x, times y, also a function of x. And that 30 there, you can kind of put it with whatever piece you want. I'm going to put it with whatever piece it's next to. So I'm thinking of this really as 30x squared times y. And similarly here, I'm thinking of this as 5x times y squared. It just makes it easier to deal with. So using the product rule here, we're going to get two pieces. The derivative of 30x squared times the not derivative of y plus the not derivative of 30x squared times the derivative of y. Let's try that again. For 5xy squared, or I should say 5x times y squared, we're also going to use the product rule. Derivative of 5x is 5 times leave y squared alone, plus switch it up, leave 5x alone. The derivative of y squared, or some stuff squared, is 2 times our stuff to the first power times the derivative of the stuff. So we get 2 times y times dy dx. Finally, equal to the derivative of -21 is 0. Cool. Okay, so yeah, let's do it this way first. So as I said, I think last time with the implicit differentiation, if you're finding the slope of the tangent line at one particular point, it's almost always the best call to plug in that point right after you differentiate both sides. So I'm going to plug in x equal to 1 and y equal to -1 right now. We plug in x equal to 1, y equal to -1. Things are going to be pretty nice. 12 times 1 squared is 12. 60 times 1 times -1 is -60. 30 times 1 squared is 30, and there's still a dy dx hanging around there. 5 times -1 squared is +5. 5 times 1 times 2 times -1 is -10 times dy dx. And then we're going to collect all the dy dx terms on one side. Let's just leave them on the side they're on. So I have a 30 dy dx and a -10 dy dx. So I have a 20 dy dx on the left. And on the right-hand side, I'm going to subtract 12 from both sides and subtract 5 from both sides and add 60 to both sides to get 60 plus 12 minus 5. Sorry, 60 minus 12 minus 5 over there, which is going to be what? 48 minus 5 is 43. Don't be sorry. Okay, so then finally, dy dx is going to equal 43 divided by 20. That would be the slope of the tangent line at the point -1, sorry, 1, -1. And then we were asked to find the equation of the tangent line. So we then have to do the thing we've been doing for the last two problems. We say that y minus the y coordinate is equal to the slope times x minus the x coordinate. I would still simplify this. I have y plus 1 equals 43 over 20 times x. And then 43 over 20 times -1 is minus 43 over 20. I'm going to subtract 1 from both sides. I'm going to subtract 20 over 20 from both sides. So I've got y equal to 43 over 20 times x. And -43 over 20 minus 20 over 20 is negative 63/20. Not the words, not the nicest numbers ever, but they're not too terrible. What if instead I had just said find dy dx? And I didn't say I didn't want to find the slope of the tangent line. Well, then if we were just finding dy dx, just find dy dx for the same jumbled up equation. Well, the first step would still be the same. We would still get all this gnarliness here. 12x squared plus 60xy plus 30x squared times dy dx. I'm going to simplify, sorry, not this term, plus 5y squared. I'm going to simplify this term a little bit and say it's 5 times 2 is 10 times x times y times dy dx equal to 0. So now the process isn't quite as numerically easy, but it's still not terrible. Sorry, I'm getting all over the place here. So then we would still isolate the dy dx terms. Leave them on one side. So I have 30x squared dy dx plus 10xy dy dx. And everything else goes to the other side. So it's going to be negative 12x squared minus 60xy minus 5y squared. 2 more steps to go. We have to factor out the dy dx here. So we have 30x squared plus 10xy. Still equal to all the same stuff, which you don't have to write, but I feel like I have to write. And finally, divide both sides by 30x squared plus 10xy to get dy dx equal to all of that. Negative 12x squared minus 60xy minus 5y squared divided by 30x squared plus 10xy. Oh, kind of gnarly. So a reminder that when we're doing implicit differentiation, we are always making the assumption that y is a function of x. So when we differentiate something like y to the second power, we get 2 times y to the first times dy dx. Because we're always multiplying by the derivative of the inside stuff, which is always just the derivative of y. Oh, I'm out of water. All right. More practice. Move it a little bit. So here's one that I've seen a couple times that I think is kind of interesting, or something like this. I've seen the problem where it's like find dy dx, given that, I don't know, something gnarly like y cubed equals 2x squared plus 4y over y. Actually, let's make that a 4y squared over y minus x squared. And although you certainly could, it is not the best choice to just start taking the derivative of both sides here. Because I really, really don't want to use the quotient rule if I don't have to. And for implicit, you almost never have to use the quotient rule. I know I've said this before, like I might have said this in class, where you can always avoid the quotient rule by like, instead of the, like, so here's what I'm not saying. Although you certainly could, I don't want to rewrite the right-hand side as 2x squared plus 4y squared times parentheses y minus x squared to the negative 1. Although that's certainly a way you could always avoid the quotient rule. What I'm saying here is for an implicit equation, right? There's always an equation here. It's always equal to something else. You can manipulate that equation before differentiating both sides. Specifically, I could multiply both sides by the denominator on the right-hand side. So that on the right-hand side, those things cancel out. On the left-hand side, I can distribute and get y cubed times y, which is y to the 4th, minus x squared times y cubed, equal to 2x squared plus 4y squared. And that looks a lot better to deal with differentiating both sides of than the original expression. So if you have some sort of fractional thing that's going to require implicit differentiation, you are totally allowed to multiply both sides by the denominator before you differentiate both sides. Not only allowed to, but I think encouraged to. This is probably the way you are meant to do a problem like this. So let's do the thing. In fact, why don't you all do the thing? I'm gonna fill up my water. Take the derivative of both sides. I'll be right back. All right. Let's start differentiating again. We're assuming y is a function of x, or y is our stuff. So if I differentiate both sides, the derivative of some stuff to the fourth is 4 times our stuff to the third times the derivative of our stuff. And you can either write dy dx or y prime, either way you like it. I find it easier to write y prime, but dy dx is perfectly good too. Over here, we have minus, and we're going to have to use the product rule. I'm going to put some parentheses around the product I'm going to get. So derivative of x squared is 2x. Leave the y cubed alone. Plus, leave the x squared alone. And the derivative of y cubed, or some stuff cubed, is 3 times my stuff squared times the derivative of my stuff. I can zoom in a little bit here, I think. On the right-hand side, the derivative of 2x squared is 4x. The derivative of 4y squared is 8 times my stuff to the first times the derivative of my stuff. Do be careful here. When you're subtracting a product, you do have to subtract the entirety of the product rule, meaning essentially each part becomes negative. So distributing this minus sign, I get 4y cubed y prime minus 2xy cubed minus, I'm going to simplify this a tiny bit. I'm really just going to write the 3 in front because that's standard, minus 3x squared y prime equal to 4x plus 8y y prime. And then we collect all the y prime terms on the same side and all the other terms on the other side. Let's bring the y primes to the left. 4y cubed y prime minus 3x squared y prime minus 8y y prime equal to 4x plus 2xy cubed. Factor out a y prime. You have 4y cubed, y prime times 4y cubed minus 3x squared minus 8y equal to 4x plus 2xy cubed. And then lastly, divide by whatever is multiplying y prime to get y prime equal to 4x plus 2xy cubed divided by 4y cubed minus 3x squared minus 8y. Typically, for these problems, when you're finding y prime using implicit differentiation, you almost never can simplify your results. Like usually there's no simplification that happens here. And even if there is, you really shouldn't. Like technically, I could factor out an x from the top and a y from the bottom. That doesn't help us. So don't, unless specifically asked to, don't even consider trying to simplify the derivative implicitly. Let's zoom back out a bit. Okay, let's kind of take a minute to review where we're at, or actually let's take a minute to review kind of the rules we have seen so far. And I'm making, gosh, I really would like to get slightly more zoomed out here. I'm making the assumption that everyone has seen at this point product, chain, quotient, and chain rule. Is that a safe? Has everyone seen the chain rule in their class? I know you've seen it here. Well, in fact, we talked about it like at no, like last week, was it right? Last week we were like all day chain rule, and we did. So we were all good with the chain rule in here. You might not talk about it in your class yet, although I think everyone has. So let's briefly review just kind of the rules we know and talk about the rules we still have to cover. So first of all, there's the differentiation rules. It's going to be brief. So we have, I guess I should mention all of them. So we have the constant rule, not the constant multiple rule, just the constant rule, which says that the derivative of a constant is equal to 0. We have the constant multiple rule, which says that the derivative of a constant times a function is equal to the constant times the derivative of the function. It's a rule we use all the time, but almost never talk about it, right? Like we use it probably 10 times today already. Like when I took the derivative of 5x squared and got 10x or something like that. We have the sum difference rule. Again, not really one that we talk about a whole lot. And I don't know why I put the slash there. I should put the slash there. Oh, well. The derivative of f of x plus g of x is just equal to f prime of x plus g prime of x. And it's true if it's addition or subtraction. And then the actual rules we use. We have the product rule, which is that the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. Or as I would say in my head, the derivative of one thing times the not derivative of the other thing, plus then you switch them and do the derivative of the not derivative of the first thing times the derivative of the other thing. It's very wordy in my head, but that's the way I say it. I feel like the quotient rule is less wordy. Quotient rule. We have the derivative of f of x divided by g of x is going to be, okay, I'm going to write it the way I say it. The bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. In most textbooks, or the way most people write this, they usually write f prime times g instead of g times f prime. It doesn't matter which order you multiply those two things, and it's the same either way. But you might write it as f prime of x times g of x minus f of x times g prime of x all over g of x squared. Same deal. And then finally, the chain rule. The derivative of f of g of x is equal to f prime of g of x times g prime of x. Or as I would highly recommend you all think of it, the derivative of f of some stuff is f prime of the stuff times the derivative of the stuff. I think those are pretty much all the derivative rules we have. Question. The constant multiple. Yeah, sorry, I abbreviated multiple. This is the constant multiple rule. That when you have the derivative of, say, like 5 times x to the third, the derivative is going to be, or it's going to be 5 times the derivative of x to the third, which is 5 times 3x squared, which is 15x squared. Other questions about any of these rules we've written down here? I would certainly say it is an expectation that you know all of these, right? Like maybe not right this moment, but soon all of these should be in your brain. You should know, someone should be able to ask you the product rule. Yeah, it's f prime times g plus f prime, f times g prime. So definitely take the time to practice these. I mean, again, really the way you practice them is by using them. If you use the product rule like 10 times in a row, you're going to know it pretty well. So practice, practice, practice until you know the rules reasonably well. The other side of this is knowing the actual like derivative formulas. So derivative formulas. We'll write down all the things we know. We're going to write down the regular versions, and we'll probably write down the chain rule versions too. First and foremost, we have our good old power rule. The derivative of x to a power is that power times x to the power minus 1. And then we have the derivative of e to the x, which is e to the x. And then we have our trig function. So we have sine of x, whose derivative is cosine of x. And the derivative of cosine of x is negative sine of x. And we have tangent of x, and the derivative of tangent of x is secant squared of x. And cotangent of x, the derivative of cotangent of x is negative cosecant squared of x. And then we have what's left, secant of x. The derivative of secant of x is secant of x times tangent of x. And cosecant of x, whose derivative is negative cosecant of x times cotangent of x. And then there's a couple more. And again, this is where I always have to, so I'm not talking to my boss. I don't love teaching 2 sections of the same class because I can never remember what I've said in one class versus the other. So I don't know if we've talked about the derivative of the natural log of x in here. I feel like we might have last week, but I don't actually know. We might not have. It might have been the other class completely. I see someone shaking their head yes, that we did. So I'm going to go ahead and say anyway, and we can also talk about it again. So we have a couple more functions here. The derivative of the natural log of x is 1 over x. And we also have the derivative of the arctangent of x, which is 1 over x squared plus 1. Or 1 plus x squared, whichever way you want to write that. And with 2 small exceptions, they're really not exceptions, they're just variations. These are all the functions we can differentiate. There's not really anything else on the list that I can think of, unless you all can think of something I'm forgetting. I don't think there's anything else. I will point out, there are other inverse trig functions, specifically inverse sine, inverse secant, inverse cosine, inverse cosecant, inverse cotangent, that you are typically not responsible for finding the derivative of. So we won't talk about arc sine or inverse sine or arc cosine or any of the other ones, unless you all tell me that your professor is talking. So I don't think should happen, but sometimes people like to do extra things because they do. And then I guess we might as well write down the chain rule version of all these because it's worth writing them down. So let's look at the following. We're really just going to write so here's the thing. In my opinion, none of us should need this second table because we should all be able to look at the nicer, simpler version of the derivative rule and replace x with stuff. And then at the end of the day, multiply by, the derivative stuff. So each of these rules, just the chain rule version is change x to some stuff, apply the rule, and then multiply by the derivative of the stuff. So instead of having x to the p, if I had some stuff to the pth power, the derivative should be, well, I'm going to replace the x over here with some stuff, get p times my stuff, the p minus 1, and then we have to multiply by the derivative of the stuff. Same deal for e to the x. If I have e to the stuff, the derivative is going to be, well, the derivative of e to the x is e to the x. Derivative of e to the stuff is e to the stuff times the derivative of the stuff. Same deal for the trig functions. The derivative of sine of some stuff is cosine of the stuff times stuff prime. By the way, if you find it tedious to write stuff so many times, you can use the letter u instead of the word stuff. That's a pretty typical choice people make. I'm going to write stuff because that's the way I say it in my head. The derivative of cosine of some stuff should be negative sine of the stuff times the derivative of the stuff. Derivative tangent of some stuff is going to be secant squared of the stuff times the derivative of the stuff. Derivative of cotangent of some stuff is going to be negative cosecant squared of the stuff times the derivative of the stuff. Derivative of secant of some stuff is always kind of funky because the stuff shows up twice. The derivative is secant of the stuff times tangent of the stuff times the derivative of the stuff. We're almost there. Derivative of cosecant of some stuff is going to be negative cosecant of the stuff times cotangent of the stuff. times the derivative of the stuff. And then finally, the derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of the stuff. People often do write this as the derivative of the stuff divided by the stuff. That's not the way I generally like to write it, because I really like to think of doing my derivative thing and then afterwards multiplying by the derivative of the stuff. But it's totally fine to simplify it as the derivative of the stuff divided by the stuff. And then lastly, the derivative of the, I don't know, I didn't mean to put another line there, but I did. Sorry, I guess I'll put a line there to make it look the same. Derivative of the arctangent of some stuff is going to be 1 over the stuff squared plus 1 times the derivative of the stuff. And again, with 2 very small exceptions, that's pretty much the entire list of derivatives you have to be able to do. And then, of course, we can make it terrible by throwing these things into something that's a chain rule or a quotient rule or a product rule and making a real large mess of things. Let me see one thing here. Let's see. Yeah, last time we did that. Right. Oh, yeah, we definitely talked about arctangent last time. Yeah, okay, cool. So last time we kind of ended by doing the derivative of arctangent, and I would have liked to, well, I would like to spend a little more time just doing a few examples where we have some chain rule kind of thing going. Yeah. So let's see what the derivative of the arctangent of e to the x plus x cubed is going to be. I'm just applying the rules I know in my head, right? I know that the derivative of the arctangent of x is 1 over x squared plus 1. Same thing. Derivative of arctangent of some stuff is 1 over the stuff squared plus 1 times the derivative of that stuff, which is e to the x plus 3x squared. Why don't you all try this one? The derivative of the arctangent of, sure, x squared divided by 1 plus sine of x. Ooh. Well, it's a little more challenging. It's gonna look a little ugly, but it's totally doable. Give it a go. All right, here's how this should look. I'm gonna give myself plenty of room here. And it's gonna be 1 over my stuff squared plus 1. So that's gonna be 1 over x squared over 1 plus sine of x squared plus 1 times the derivative of x squared over 1 plus sine of x. So you might, if you didn't feel like doing that all at once, just write this. The downside is now I have to write it all again so that I get the right answer, but I at least got to hold off on taking the derivative of this quotient. Now that's going to equal 1 over all that x squared over 1 plus sine of x quantity squared plus 1 times the derivative of all this. I'm going to use the quotient rule for. It's going to be the bottom 1 plus sine of x times the derivative of the top 2x minus the top x squared times the derivative of the bottom, which is cosine of x. I don't need parentheses there because it's just one thing times another thing. There isn't something added to something else that have parentheses around. And then finally, over 1 plus sine of x quantity squared. Kind of gross. All right. So chain rule is in effect all the time. We just kind of look at our thing and ask ourselves, are we differentiating something that's straightforward function of x, or is it a function of something more complicated than x? I should also mention, technically you use the chain rule even if it was the derivative, like for example, if I said just what's the derivative of the arctangent of x, you could still pretend like x was your stuff and say, oh, well, it's 1 over my stuff squared plus 1 times the derivative of my stuff. So the chain rule works even if your inside stuff is just x. Yeah, let's go back that way. So I did mention a couple things. There were a couple other differentiation formula that we hadn't quite gotten to. And they kind of come from this idea of logarithmic differentiation, which is also in this section. I feel like some of these sections I feel like have just a million things in them. Yep, it sure does. Okay. So let's talk about, we want to find the derivative of 6 to the x. Which I don't think we've talked about yet, but again, it's always hard to know exactly. Here's what I want you to notice. 6 to the x is a function that's very similar to e to the x, right? E to the x looks kind of like this. Got an intercept at 0, 1. 6 to the x looks pretty much the same. It's just a bit steeper. Still has an intercept at 0, 1, but it just gets bigger faster. And if functions look pretty much the same, we shouldn't be surprised that their derivatives or rates of change are also pretty much the same. But how do we find the derivative of 6 to the x? Well, there's two ways of doing this. I'm going to show you at least one of them. So here's how I'm going to think about doing it. We're going to let y equal 6 to the x. And often when we have a function where you have a variable in the exponent, we don't really want the variable in the exponent. Like if it was e to the x, sure, we could take the derivative and get e to the x. But when I have 6 to the x, what I really want to do is take the natural log of both sides. Because that's going to allow me to get my x out of the exponent. So I'm going to take the natural log of y equal to the natural log of 6 to the x, and then bring the x down. That's why I took the natural log of both sides in the first place. Now I have the natural log of y equal to x times the natural log of 6. All right, well, now we're going to, just like any other implicit differentiation problem, we're going to take the derivative of both sides. The derivative of the natural log of y is 1 over my stuff times the derivative of my stuff. And the derivative of x times natural log of 6 is just natural log of 6. But if you don't believe me, let me ask you a couple questions. What's the derivative of 5x? 5, right? It's a straight line, slope is 5. What's the derivative of x times 4? It's still 4, right? Even though it kind of wrote it in a weird way, like no one would ever actually write x times 4. You write 4 times x. Order of multiplication doesn't matter. The derivative is still 4. And it doesn't matter if your constant there is weird or normal, like 4, well, normal, typical, like 4, or atypical, like, I don't know, e to the third power. E to the third is still a constant. it's 20, I don't know, 27 or 25-ish, somewhere around there. But if you're taking the derivative of x times a constant, you're always just going to get that constant, whether it's a nice looking one or a less than nice looking one. Well, that's also true over here. We have x times a constant, right? Natural log of 6. Do you see any x's in there? I don't. If you don't see any variables in there, it's a constant. And if you're taking the derivative of x times a constant, you're just going to get that constant. And now we solve for y prime because we're trying to find the derivative. So then we're going to say that y prime is equal to multiply both sides by y. You get y times natural log of 6. But I really don't want to write my derivative of 6 to the x as something with y in it. If my original function is a function of x, my derivative should also be able to be written as a function of x. Unfortunately, I know what y is equal to. Y is equal to 6 to the x. So we're going to rewrite our y prime, which is the derivative of 6 to the x, is going to be our y times the natural log of 6. This is the way I prefer to do this problem because actually it shows us the process of logarithmic differentiation. But I will point out there's another way to do this, which I also think is valid. And so lots of other people like to do it this other way. Let me show you another one, and then we'll talk about a rule. So let's say I wanted to find the derivative of, let's see, I don't want this. Let's make it a little bit more interesting. Let's say we want to find the derivative of 5 to the x squared. Here's what I'm expecting to happen. I just took the derivative of 6 to the x and got 6 to the x times natural log of 6. I would expect the derivative of 5 to the x, just x, to be 5 to the x times natural log of 5. And then if I replace my x with some stuff, I would expect to get 5 to the stuff times natural log of 5 times the derivative of the stuff. We'll talk about that more in a second, but let's actually do this. So we're going to do this. We're not going to do this the same way. We're taking the natural log of both sides of a thing. We're going to rewrite this as the derivative of e to the natural log of 5 to the x squared, which is also a totally valid way of doing it. I'm just biased against it. This is not how I like to do it. Totally fine. You don't have to like everything. Not everybody likes all the same things. So then we bring the x squared down. You get the derivative of e to the x squared times natural log of 5. I will remind you once again, the natural log of 5 is a constant, just like the natural log of 6 was a constant. So when we take the derivative of this e to the stuff, the derivative of e to the stuff is going to be e to the same stuff times the derivative of that stuff. And the derivative of x squared times a constant is 2x times the constant. Now, I don't want to leave my answer like this because it is noteworthy that e to the x squared times natural log of 5 is the same as e to the natural log of 5 to the x squared, which is the same as 5 to the x squared power. So all those things I've underlined in red are the same. I'm going to rewrite this as 5 to the x squared times 2x times natural log of 5. Or, as I would encourage you to think of this, the derivative of 5 to the stuff ended up being 5 to the stuff times the derivative of the stuff times the natural log of the base 5. And that actually kind of shows us what our general formula is for taking a derivative of something with a different base raised to the x power. So I'm going to write down like 4 formulas, but they're really all one formula. Here's the basic one. The derivative of b to the x is b to the x times natural log of b. That's your more general version of the formula. Whereas, that's actually your more basic version. Versus, well, no, yeah. Sorry, I meant to start off with the derivative of e to the x is just e to the x. You could also write times natural log of e, but we don't because the natural log of e is 1. And then we have the more complicated version. We know that the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And similarly, for a different base, the derivative of b to the stuff is going to be b to the stuff times natural log of b times the derivative of the stuff. So b to the stuff times the natural log of b times the derivative of the stuff. So these are the kind of the two, well, this is one of the rules I was alluding to that we hadn't quite talked about. We've already kind of talked about it, but this is just a slightly more generalized version of it. So really, when you have something like, for example, the derivative of 4 to the x cubed plus cosine of x, I'm really thinking of it in my head as like it's e to the stuff. I know that the derivative of e to the x is e to the x. I know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And then if it's a different base, I know the derivative of a different base to the stuff is that base to the stuff times the derivative of the stuff. And then I also have to multiply by the natural log of that base. It's kind of I won't lie, it feels like a lot to remember, but it's not that bad if you've built it up from things we already know. Yeah. I think we use it in A. I'm looking at let's see here. Good question. Now I know there's a question in here about the other thing I was going to say. You might be right that we don't actually see a lot of this, but might as well be complete. So, but I will point out the other thing I'm going to say about other things with different bases, there are examples of that. So it kind of behooves us to do this one first. If we're going to take the derivative of this, it's going to be 4 to the stuff. So 4 to the x cubed plus cosine x times the derivative of the stuff, which is 3x squared minus sine of x times the natural log of the base. And then there's the flip side of things, meaning there's also logarithms with different bases. And a very similar thing happens. So just like here, when you change the base, you essentially just end up multiplying by the natural log of that base. When you change the base of a logarithm, we're going to end up dividing by the natural log of that base, which I think is kind of cool. But there's this very nice kind of correlation between changing the base for an exponential and changing the base for a logarithm. Let me show you. Let's start off with a not terrible example. So let's say we want to find y prime for y equal to the log base 3 of x. So here's how we're going to do it. We're going to rewrite this equation as an exponential equation. What's our base? Not everyone at once. What's our base? It's 3. What's our power or exponent? Ooh, is it y or is it x? Let me remind you all my favorite logarithmic equation. Log base 2 of 8 equals 3. The base is 2. The exponent is 8 or 3. Definitely 3, right? Because 2 to the third power is equal to 8. So the entire logarithm is equal to the exponent we're looking for. So in this case, it's 3 to the y is equal to x. And now we're going to use the rules we just talked about to take the derivative of both sides. I know that the derivative of 3 to the stuff is 3 to the stuff times the derivative of the stuff times the natural log of 3. So check it out. If we differentiate both sides, we're going to get 3 to the stuff times the derivative of the stuff times the natural log of the base. On the right-hand side, the derivative of x is going to be just 1. And now, just like before, we're going to solve for y prime. So y prime is going to equal 1 over 3 to the y times natural log of 3. But then we can replace the 3 to the y with what it's equal to, which is x. So we can say, oh, look, y prime is really 1 over x times natural log of 3. So here's what we found. We found that the derivative of log base 3 of x is equal to 1 over x natural log of 3. Which I don't think is too surprising because we knew that the derivative of the natural log of x was just 1 over x. So all changing the base did was still give us a 1 over x as our derivative, and then we're also having division by the natural log of 3, or multiplication by natural log of 3 in the denominator, which is division by natural log of 3. So the general rule here is that the derivative of log base b of x is 1 over x times natural log of b. And then the more general rule, if it's a chain rule kind of deal, is that the derivative of log base b of some stuff is going to be 1 over the stuff times the derivative of the stuff, and then dividing by the natural log of the base. Which looks kind of gross, but it is what it is. So those are the other rules I was referring to. If you have an exponential function or a logarithmic function with a different base, we either have to multiply by the natural log of that base if it's exponential, or divide by the natural log of that base if it's logarithmic. It probably won't come up very often, but it could come up occasionally. Now we've really talked about all the derivative rules. Nothing left. We're all done. Go home now. There's lots of stuff left. There's lots of application left. Actually, well, no, we have talked about all the rules, but there's one more process we have to talk about. And yeah, and we're in the section for that. So let's talk about the following. I want to find the derivative of x to the x. I'll tell you right now, we cannot use the power rule because it's not x to, say, the 5th or the 7th. It's not x to a number. It's x to the x. Similarly, we can't use the derivative of an exponential function rule because it's not like 2 to the x or 3 to the x or e to the x. It's a variable to the x. And so this is where we're going to have to use this process of logarithmic differentiation that we've already used a couple times, where we take the log of both sides and then do some stuff and then take the derivative. So let's go through the process here. So this is the process. We're going to use what's called logarithmic differentiation. Sometimes we use this even though we don't have to, but here we kind of have to. If you have a variable in your base and in your exponent, you kind of have to use logarithmic differentiation. So step one, we're going to first write it as an equation. So we're going to write not just x to the x, we're going to write y equals x to the x, because we have to have two sides of an equation that we can take the natural log of both sides of the equation. Step two, take the natural log of both sides. So we're going to get the natural log of y equal to the natural log of x to the x. Step three, simplify the right-hand side. Typically by bringing down whatever your exponent was in front of the natural log. So we're going to rewrite this as the natural log of y equal to x times the natural log of x. Step four, differentiate both sides. Again, making the assumption that y is, well, it's not even an assumption here. It is fact. Look up here at step one. Y is a function of x. So when we take the derivative of both sides, y really is some stuff, and we're going to use implicit differentiation to take the derivative of the natural log of y. We're going to get 1 over our stuff times the derivative of our stuff. On the right-hand side, and this is true for these problems almost always, you almost always have to use the product rule when you take the derivative of the right-hand side, because your power came down as a variable, and your natural log of some stuff is also a variable. So we have a function of x times a function of x. So using the product rule, it's going to be 1 times leave natural log of x alone, plus x times the derivative of the natural log of x is 1 over x. These next two steps, I feel like you can combine into one step, but I'm going to write them as two steps. So step 5, we're going to multiply both sides by y. And also simplify the right-hand side if you can. So we're going to get y prime on the left equal to y times the natural log of x plus x times 1 over x is just 1. Finally, replace y with what it's equal to. In this case, x to the x. So we're going to get y prime equal to x to the x times the natural log of x plus 1. And that's our final answer. So the derivative of x to the x is x to the x times, parentheses, the natural log of x plus 1. There is a really gross, stupid formula you can memorize. In my over 20, 30 years of doing math with derivatives, I don't know, however long it's been, I've never memorized that formula. You should not memorize that formula because it's really hard to remember and you should know this process instead. Yeah. Step 4 says differentiate both sides. Or take the derivative of both sides. Let's do another one. How much time have we got? Yeah, we got 15 minutes. Okay, it's not all going away. So let's do the following. Let's find the derivative. Oh, I also point out, it's cruel of me to write it this way. I'll say again, not cool, cruel. It is unkind to find the derivative of x to the sine of x. A nicer way of writing this question, like in the textbook, would be to say, find y prime for y equal to x to the sine of x. If it's written this way, you're a little more clued into the fact that, oh, I have a y equal to a thing, and I need to take the natural log of both sides. If they don't write it that way, you have to recognize, oh, my base and my exponent both have a variable, and to be able to deal with that, I have to be able to take the natural log of both sides, and to have both sides, I have to rewrite it as y equal to x to the sine of x. So if you see this, you need to start by saying, okay, yeah, I need y equal to x to the sine of x. Okay. Yeah, we got enough. So we're going to, again, take the natural log of both sides. So the natural log of y equals the natural log of x to the sine of x. We're going to bring down the powers. So the natural log of y is going to equal the sine of x times the natural log of x. Notice on the right-hand side, it's a function of x times a function of x, so we're going to have to use the product rule when we take the derivative. Step 4, differentiate both sides. Left-hand side is always going to be natural log of y. So when you differentiate it, it's always going to end up being, the derivative is going to be 1 over y times y prime. Every time for this kind of process. So we're going to get 1 over y times y prime. On the right-hand side, product rule, derivative of sine of x is cosine of x. Leave the natural log of x alone. Plus, then you switch it up, leave the sine of x alone, multiply by the derivative of the natural log of x, which is 1 over x. Multiply both sides by y. Again, I feel like you can skip this step. Instead of writing y prime equals y times all of this, you can write y prime equals x to the sine x times all of that, but it's also fine to not skip the step. Y prime equals y times, I do want to, well, there's not really much simplification to do here. The only real simplification I can do is to rewrite sine of x times 1 over x as sine of x divided by x. And then finally, we can rewrite, or we can replace y with what it's equal to. So we can say that y prime is equal to x to the sine of x times all of this. Cosine of x times natural log of x plus sine of x divided by x. Kind of a gnarly process, but very useful. Questions about that one? Okay. Let's see what else I want to say. Oh yeah, I know what I want to say. So for ones like this where you have a variable raised to a variable, we have to use logarithmic differentiation. But sometimes your derivative is just so gnarly in the first place that you want to use it even though you don't require it. So let's look at another example where we're going to be told to use logarithmic differentiation even though you can get away without doing it. Let's say we have the following. So we want to use logarithmic differentiation to find dy dx for y equal to x to the fifth times tangent cubed of x over, sure, that's almost not gross enough, x cubed plus 1 to the fourth power times, sure, e to the 7x. So you could totally do this problem without using logarithmic differentiation, and it would be awful. Right, the derivative, you'd have to use the quotient rule and the product rule twice and the chain rule a couple times, and it would just be real gross. So instead, for something like this, if we're told to use logarithmic differentiation, we're going to do it. So we're going to take the natural log of both sides. And the whole reason we're doing this is so that if you have the natural log of a product or a quotient, you can simplify that into many easier to deal with logarithms. So we're going to break up the natural log of x to the fifth times tangent cubed over x cubed plus 1 to the fourth times e to the 7x as, well, let's see. So first I'm going to say it's the natural log of x to the fifth times tangent cubed x minus the natural log of x cubed plus 1 to the fourth times e to the 7x. And then we're going to break each of those logarithms of products apart as the sum of two logarithms. This is going to be the natural log of x to the fifth plus the natural log of tangent cubed of x minus, be careful here, I'm going to break this up as a product, but it's minus the entire thing. So it's minus the natural log of x cubed plus 1 to the fourth plus the natural log of e to the 7x. That minus sign will distribute to each of those terms. Okay, we've broken it up into as many logarithms as possible, but we have one more thing we can do. We can bring down any powers in front. So I should rewrite this as the 5 times the natural log of x plus 3 times the natural log of the tangent of x minus 4 times the natural log of x cubed plus 1 minus, right, because the minus sign distributes, 7x times the natural log of e. And the natural log of e is just 1. So then we're finally ready to differentiate both sides. So now we're going to differentiate both sides. Just like the two previous times, the derivative of the natural log of y is going to be 1 over y times the derivative of y. On the right-hand side, a lot of things to do here. So the derivative of 5 times natural log of x is 5 times 1 over x. The derivative of 3 times the natural log of some stuff is 3 times 1 over the stuff times the derivative of the stuff. Same deal here. Minus 4 times the derivative of the natural log of x cubed plus 1 is 1 over x cubed plus 1 times the derivative of x cubed plus 1. And finally, the derivative of negative 7x is just minus 7. Okay, we're almost done. We still have to multiply both sides by y. Here I am going to skip that step. Instead of writing y prime equals y times all of this, I'm going to replace y with what it's actually equal to and write, okay, y prime is equal to y times all of that. I am going to simplify this a little bit. 5 times 1 over x is 5 over x. 3 times 1 over tangent times secant squared is 3 secant squared of x divided by tangent of x. Minus 4 times 3x squared is 12x squared over x cubed plus 1 minus 7. And then the y here is going to be the x to the 5th times tangent cubed x divided by x cubed plus 1 to the 4th times e to the 7x. Oops, sorry, I can't quite see that. Apologies. It's not my favorite thing to do, right? These problems are kind of really super funky, but it is better to do it this way than to have tried to just differentiate this directly. In my opinion, the better kind of question to ask is to give you something like the following. Is to say, hey, find the derivative of the natural log of something gross, like x to the 3rd times sine to the 4th of x divided by x squared plus 1 to the 7th times cotangent of x. To me, this is a little less terrible because you don't have to do the whole thing of first taking the natural log of both sides, right? So here you're actually not using logarithmic differentiation. You're just going to use the fact that you're taking the derivative of a logarithm of something terrible and break it up into many less terrible pieces. I will also point out, because this happens all the time, when you break up a logarithm of a quotient of some products, it breaks up into all its factors, right? The factors are x to the 5th, tangent cubed, x cubed plus 1 to the 4th, and e to the 7x. Every factor in the numerator ends up with a positive logarithm. Every factor in the denominator ends up with a negative logarithm. And that is always the case. So I'm not going to jump to it, but I'm going to tell you, you could skip this first step or two that I'm doing and jump straight to the end and say, okay, well, first I'm going to simplify. So I'm going to rewrite this as the derivative of the natural log of the top minus the natural log of the bottom. And then each of these we're going to break up. The natural log of x cubed times sine to the 4th is going to be the natural log of x cubed plus the natural log of sine to the 4th. Similarly here, the natural log of x squared plus 1 to the 7th times cotangent of x is going to be the natural log of x squared plus 1 to the 7th plus the natural log of cotangent of x. But it's minus all of that. Bringing down the powers and distributing the minus sign, I get 3 times natural log of x. I get 4 times the natural log of sine of x. I get minus 7 times the natural log of x squared plus 1. And I get minus the natural log of cotangent of x. And now finally, we've simplified it as much as we can. Now we're going to take the derivative of this whole thing. So I've been writing this ddx symbol each time to remind myself, oh yeah, I still have to take the derivative. That's what that ddx means. So now we're going to differentiate and get 3 times 1 over x plus 4 times 1 over sine of x times the derivative of sine of x, which is cosine of x, minus 7 times 1 over x squared plus 1 times 2x minus 1 over cotangent of x times the derivative of cotangent, which is negative cosecant squared of x. And I would not bother to simplify this unless someone told me to. All right, it's 3:26. I'm beat. Call it a day.